In this video, we're going to talk about double replacement reactions. So in a double replacement reaction, two things replace each other. Reactants must always be two ionic compounds in an aqueous solution. So here's an example: sodium hydroxide aqueous plus iron 3 chloride aqueous. So I'm going to change each cation and anion in these ionic compounds to a different color to help you visualize what's happening here. Okay, so step one is to assign all the charges. So the charges are what they are, and they're correct. They gave them to you in the reactants. But if you do this work up front, you won't have to do it when you do the products because it'll already be done, and you'll have a better chance of knowing it's correct. So I always like to do the charges first. So sodium's in group 1, so that's a +1 charge. Hydroxide is a polyatomic ion from table E, and it has a -1 charge. So those balance. That's why there's no subscripts there. Next, we have FeCl3. So the Fe can be a couple of different things, but because it's Cl3, Cl is -1, that means this Fe must be +3 to balance it out. So 3 plus is balanced out by 3 -1s. Okay, step 2 is to do the double replacement. Now you can think about it either way, as the two metals switch places or the two non-metal switch places. It doesn't really matter because you're going to get the same answer either way. I tend to think about it as the metals switch places. So the red element here is going to take the place of the green element, or the green element is going to take the place of the red element. So I'll write Na, and because I've done the charges already, I'm just going to bring them with me when I write the products. Na with its +1 charge is now going to partner up with Cl, chloride, with its -1 charge. The Fe with its 3 plus charge will now pair up with the OH, hydroxide, with its -1 charge. Step 3 is to crisscross the charges for your products. No need to do it for your reactants because it's already been done for you. They've given you correct reactants, but you don't have the correct products necessarily yet until you crisscross. So no need to crisscross in our first product, +1, -1, that balances, but I do in my second product. 3 plus does not balance out a -1, so I'm going to cross this 3 over here. Remember, when you are indicating that you have more than one polyatomic ion, you have to write parentheses around your polyatomic ion. So FeOH like this in parentheses, then the 3. And then step 4 is to balance your equation. So I have 3 hydroxides on the right and 1 on the left, so I'll put a little 3 there. That gives me 3 sodiums on the left, only 1 on the right, so I'll put a 3 there. I now have 3 chlorines on the right, 3 chlorines on the left, 1 iron on the left, 1 iron on the right. So we're good. Double replacement reactions have certain driving forces or reasons that they will happen or not happen. So they will only happen if one of the products is either a product that doesn't dissolve in water and forms a solid. Another way of saying that is a precipitate. If one of the products is a precipitate, that means a reaction will happen. And 9 times out of 10, this is the one that's going to happen in the double replacement reactions that you see. Another driving force is if you produce a gas that bubbles out of solution, or if you produce a molecular compound, which is usually water. So let's complete the following double replacement reactions and balance them. We're going to right now assume that all the reactions actually take place. So I want you to go ahead and write these down in your notebook and give them a try. So remember our steps. The first thing we want to do is write the charges for everything. Then we do the double replacement, either the two metal switch places or the two non-metal switch places, your choice. Bring the charges with you, crisscross, and then balance. Okay, here's the first one. So Ca gets a +2 charge, chlorine is a -1 charge. Sodium is +1 and hydroxide is -1. So let's do the double replacement. The Ca and the Na are going to switch places. It doesn't matter which one you do first. Either way is equally correct. I'll do the Ca first with its 2+ charge. We'll partner up with hydroxide with its -1 charge, and we need to crisscross the 2 to balance that. So either crisscross while you go or crisscross at the end, it doesn't matter, your choice. The sodium with its +1 charge will partner up with the chloride with its -1 charge. Notice I just brought over chloride at it. Because it was a 2 over here doesn't necessarily mean it's a 2 over here. I'm just going to write chloride with its charge, and I'll crisscross later and see if I need it. And this one I don't. A +1 balances out a -1. Okay, and then the last step is to balance. This isn't balanced, so let's go ahead and balance it. I will put a 2 over here to balance out the hydroxides. 2 hydroxides now on the left and 2 on the right. And my sodiums aren't balanced, so I'll put a 2 over here, 2 sodiums on the left, 2 on the right, and now my chlorines are balanced. 2 chlorines on the right and 2 on the left. Okay, for the next one, Cu is a tough one. It can be +1 or +2. Let's figure it out from the anion. So the anion is chloride, and I have 2 of them. So chlorine or chloride is always -1. So 2 -1s gives me a -2 on the anion side, which means the cation has to be the +2 variety. So potassium is in group 1, so it gets a +1, and sulfide is in group 16, so it gets a 2-. So 2 +1s balances out 1, 2-. So let's now do the double replacement. Copper 2 is now going to partner up with sulfide with its 2- charge. And potassium with its 1+ charge is now going to pair up with chloride with its -1 charge. So no need to crisscross, but we do need to balance. On the left, I have 2 chlorines and 2 potassiums. On the right, I only have 1 of each of those things, so that's an easy fix with the 2 there. Let's check our sulfurs balance and our coppers balance as well. So we're done with this one. Okay, last one. Potassium gets a +1 because it's in group 1. Hydroxides on table E, it's -1. Iron is, we're going to figure that out from the anion. Nitrate, NO3, is -1. I have 3 of those, so 3 -1s is a -3, so that means this iron must be +3. Okay, let's do the double replacement. Potassium with its +1 charge is now partnered up with nitrate with its -1 charge. And then iron with its +3 is now partnered up with hydroxide with its -1. That doesn't balance, so I'm going to crisscross the 3 over here. So my product is FeOH3. Okay, this isn't balanced, so I'll do that by putting the 3 here. 3 OHs on the left. Now balance out my 3 OHs on the right. I have 3 Ks on the left and only 1 K on the right, so I'll put a 3 there, which will fix the NO3s as well. I now have 3 NO3s, and then over here I have 3 NO3s. 1 iron, 1 iron, we're good. Okay, so far we've learned 4 types of reactions, and remember we recognize them from their reactants. So if I have an element plus an element, that's going to be a combination or a synthesis reaction. If I just have a compound and nothing else on the left, that's automatically a decomposition reaction. If I have an element plus a compound, that's going to be a single replacement reaction. Remember, you always check table J. And if I have 2 compounds, that is our double replacement reaction. So I'd like you to pause the video and try to identify these as what type of reaction they are. And then when we're done, I'll tell you the answers, and then we will solve them. Okay, let's see how you did. We have combination. I have an element plus an element. That's easy, that's a combination. The next one is just a compound on the left, and it's showing it's being heated, so that's obviously a decomposition. Whenever you only have one reactant, it's only one thing it can be is decomposition. Next I have zinc, an element, plus H2SO4, a compound. Whenever I have an element plus a compound, that is a single replacement reaction. Next, I have another decomposition, just a compound breaking down electricity, that's decomposition. Next, I have another single replacement, a little trickier because the element that's doing the replacing is on the right. It's the second reactant rather than the first, but it doesn't matter. This nonmetal is going to try to replace this nonmetal. It's a single replacement. And then I have a compound, silver nitrate plus sodium chloride, another compound, that's double replacement. And then last I have another double replacement, compound plus compound, double replacement. So how'd you do? Did you answer them all? Probably. Next, a little harder than just identifying what type they are, I'd like you to solve for the products of these things. So again, take some time, pause the video, and see if you can come up with the correct answers for these. Okay, for the first one, we're going to combine the H and the O, and we either get H2O as water, or some of you might have H2O2. Both answers are equally good here. Next one, this water is going to decompose or break down into its elements, H2 plus O2. I'm not going to balance any of these just to save time. Hopefully when you solve them, you balance them. Next, we have zinc taking the place of hydrogen. You're going to get zinc sulfate and hydrogen H2 as our products. Next, the HgO is going to decompose or break down to Hg and O2. Remember, O2 is diatomic, so it always has to be paired up with another oxygen. Next is a single replacement. This chlorine is going to try to take the place of this bromine. Hope you checked table J, because it will happen. The K is now going to be partnered up with the Cl, and then bromine is going to be by itself, but again it's diatomic, so it's going to be Br2. Next, we have our two double replacement reactions, our two metal switch places, or our two non-metal switch places. I hope you assigned the charges first and then did the double replacement and crisscrossed if you needed it. Our two products are going to be AgCl and NaNO3. And our products for our last double replacement are going to be water, HOH. Okay, so let's summarize what we've learned in this video. In a double replacement reaction, two elements from two compounds switch places. So if I have this compound AB plus the other compound CD, the A and the C are going to switch places, and the A will now be paired up with D, and the C will now be paired up with B. You can think about it as the two metal swap partners or the two non-metal swap partners. It doesn't matter, you'll get the same answer either way. A double replacement has certain driving forces that determine if they'll happen. Most notably, whether they form a solid precipitate or not. We'll talk about that in an upcoming video. And to solve a double replacement reaction, you just need to follow the four-step approach that we've learned here. So step number one, I like to assign all the charges. Step number two, I like to do the double replacement. Step number three, I crisscross the charges of my products. And step number four is to balance. And if you do this, double replacement reactions should be no problem.